Hello, in this video we're going to be looking at finding the area between two curves that are given in polar coordinates. So let's look at this example here. Find the area inside the curve r equals 3 cosine theta and outside the curve r equals 1 plus cosine of theta. So the first thing to do is to graph them. I use GeoGebra to graph these, but you can use whatever graphing utility you have. You could do it by hand if you wanted to, but here I use some technology. And we want to find the area. So this is the inner curve, 1 plus cosine of theta is this cardioid here, heart-shaped curve. And we want outside of that, but inside this 3 cosine of theta, which is a circle of diameter 3 here. So we're talking about this area right in here, kind of a crescent shape. One of the things we need to do is find these points of intersection here and here, and we want to do it in such a way that we can graph these curves over a continuous values of theta from some theta here around to some theta here, and hopefully trace through that graph once, and hopefully trace through this one once at the same theta values. And if you look, since this is in the fourth quadrant and this is in the first quadrant, something between, say, negative pi over 2 and pi over 2 would be an appropriate range. Of course, we won't go as far as pi over 2 or as far down as negative pi over 2, but we'll have to figure out what it is for these angles going to that point of intersection and that one there. All right, so we can find those points of intersection by setting the two curves equal to each other and solving this. So subtracting cosine of theta from both sides, 3 cosine theta minus 1 cosine theta is 2 cosine theta. Of course, that eliminates on that term on the right, which was the point. To get rid of the 2 here, we divide both sides by 2, leaving cosine of theta on the left, 1/2 on the right. So we want an angle whose cosine is 1/2. That is, x over r is 1 over 2 for a point on the circle. So if you look here, we want an x of 1 and an r of 2, where we have this triangle right here for our reference triangle, 1, square root of 3, and 2, and that's embedded in a circle of radius 2 centered at the origin will give us that point. And notice we have x, y, and r coordinates there, specifically an x of 1 and an r of 2, and the theta there, the angle, is pi over 3. You should probably recognize this as a special triangle that you've seen a lot in trigonometry, pre-calculus, and calculus, and so forth. This is a pi over 6, pi over 3, pi over 2 triangle, or in other words, 30 degree, 60 degree, 90 degree triangle. Of course, this triangle could be flipped over into the fourth quadrant down here, and again, we still have an x of 1 and an r of 2. The y is just negative square root of 3 down here, where it's positive square root of 3 up here. So in any event, the two angles we're looking for are plus or minus the square root of 3. And so now if you should probably do this with your graphing utility, actually graph these curves, but only graph them from a theta of negative pi over 3 right here around to a theta of positive pi over 3 right here. And I did that for both curves here. And you see that it does trace out the boundaries of the region that we want to find the area of. All right, so let's set up our integral. Okay, so if you're thinking about approximating this, we're talking about approximating this with little sectors, circular sectors. And if we were approximating the integral of the outer curve, then we're looking at this blue region plus the green region right here together for one of your slices. As we do more and more of those slices, it approaches this here. So the outer integral from minus pi over 3 to pi over 3 of this outer curve is the total area of the blue and yellow together. And then if we subtract off the yellow area, which is the integral of the inner curve, we get the thing we're looking for. So if big R is the R value for the outer curve, in this case the 3 cosine theta, Then 1/2 r squared d theta, as we saw in our previous video, from theta 1 to theta 2 is that area. Then we want to subtract from that the area here to get the remaining leftover area that we're wanting. And little r is the value here. So it's we can combine this as one integral by factoring out the 1/2. And then we have 1/2, the integral from theta 1 to theta 2 of big R squared minus little r squared d theta, where big R is the radius on the outer curve, little r is the radius on the inner curve. Now, of course, these r's are, both of them are functions of theta. Specifically, the big R is 3 cosine theta. The little r is 1 plus cosine of theta. And we're going to square both of those, subtract, and then integrate from minus power 3 to power 3. Now I'm going to make use of some symmetry here. I think you can see by looking at this particular curve that the area is equal above and below the x-axis. So if we just start from the x-axis of theta of 0 and go up to power 3, find that area, if we would just double that, then that will be the integral that will give us the area that we want. So doubling this will change the 1/2 to a 1. And now our limits now go from 0 to power 3. So we're going to work with that version of the integral right there. So working that out, here's what happens. Let's work out the details. Square this, you get 9 cosine square of theta. Squaring this and distributing the 1. So you get 1 squares 1, that makes it a minus 1. Multiply and double to get 2 cosine theta, that makes it minus 2 cosine theta. Square that term, cosine square. That makes it minus cosine square. Combine like terms here. 9 cosine square of theta minus 1 cosine square theta is 8 cosine square theta. Then we've got minus 2 cosine of theta and then minus 1. So we need to break this into 3 integrals. The integral of the last part is just minus the integral of d theta. The integral of this part is minus 2 integral cosine theta, and then you've got this 8 cosine square theta. Cosine square theta, you remember from our techniques of integration, needs to be integrated by changing with a power reducing identity or double angle identity, which reduces the power down from 2 to 1. The way that works is cosine square theta is 1/2 times parentheses 1 plus cosine of 2 theta. You double that angle. Now let's see, this is a 4 here. 8 times a half is a 4. Distribute that. That gives us 4 d theta plus 4 cosine of 2 theta. Now cosine of 2 theta d theta, we want really is cosine u du. If u is 2 theta, du is 2 d theta. So we can put a 2 here if we put a 1/2 here. Now we had a 4, so 4 times 1/2 gives us the 2 here. Now the 4 d theta here minus 1 d theta here is 3 d theta. 3 times the integral of d theta, I should say. All right, so now we have our 3 integrals. The antiderivative of d theta is just theta. Antiderivative of cosine u du is sine of u, u being 2 theta. And the antiderivative of cosine theta is minus sine, no, it's positive sine of theta, and the minus comes from here. Now we evaluate from 0 to pi over 3, means we take this thing right here, we put in pi over 3 in place of theta, minus, put in 0 in place of theta here. And let's just simplify. 3 times pi over 3 is pi. 2 sine of 2 times pi over 3. Well, 2 pi over 3 is actually, if you put that in standard position, that puts us back in the second quadrant, but it's just a mirror image of this picture here. So it's the same triangle flipped over. So it's square root of 3 up, 1 to the left, and 2 for the hypotenuse. And the sine is the square root of 3 over 2. In other words, y over r, square root of 3 over 2. So that's square root of 3 over 2 for that. The sine of pi over 3, that's also square root of 3 over 2. That's this triangle here, and it's square root of 3 over 2 for that one. All right, so that gives us that, and then the rest of it's 0. 3 times 0 is 0, 2 times 0 is 0, sine of 0 is 0, again, sine of 0, 0. So this part just goes away. And look at these two parts. This part and this part are exactly the same size but opposite in sign. They're going to cancel each other out. And when the dust settles, I'm left with just pi. And here is, that's verified by this here. So we can see that that's verified by the TI Nspire CAS. And we see that that blue area there is approximately 3.14, which is an approximation of pi, with this approximation techniques used in this this applet here. And so that's how you can set up an area between two curves as a single integral using polar coordinates.